The other thing is places like that, if there's a lot of pencil, it's definitely
Aiden, do you want to play pickleball?
Absolutely.
Grand finale.
Yep. Time for the big fireworks ending. Mic on?
Yeah,
Microphone on?
I think so.
I scrambled the flat iron today. Oh, today? Too many. It was pending for a long time. Yeah, I didn't die, yeah. But I was slower than I thought I would be.
Ethan.
But it was still fun. But I think for people who
Yeah, just kind of watching people come in.
psychologically, physically.
I got
Sounds good. All right. Should we be going, Tom?
Yep.
All right, let's get started for the very last session. Tom Hartman's going to tell us something about C-theorems. Take it away, Tom.
All right. So C-theorems. I've written up a couple things so that we can get to the end, but this is just the introduction. So C-theorems are an idea about organizing the space of quantum field theories. Okay, so what we're interested in from the point of view of the bootstrap and also in individual theories that we're interested in the real world is understanding how different theories are related to each other and what can happen in the space of theories. And the C-theorems are sort of an organizing principle for that space of theories. A quantum field theory, and I'm distinguishing here between QFT, which is not conformal, and CFT, which is conformal. But a QFT is a theory with a mass scale. And QFTs that are completely self-consistent by themselves are RG flows between two conformal fixed points. Conformal fixed point in the ultraviolet and a conformal fixed point in the infrared. So the QFT is, I see some shaking heads, but what's the objection?
Just because there's a Gaussian fixed point out there doesn't mean that QCD is particularly conformal. And the bottom line right there, I guess, is what atomic physicists do. So
so in QCD, the bottom one is the nothing theory.
yeah,
So that's conformal.
It's Gilla, right? It's protons.
Yes. Well, protons are here. This is the nothing theory. But it's true that we have to be careful about things like running in the UV, but I would count the free theory as a UV fixed point in that case. Okay, so so the QFT is the whole thing. And roughly speaking, if we take some correlation functions in the QFT and we evaluate them at momenta that are much bigger than the mass scale associated to the RG flow, those correlation functions will agree with the UV fixed point. And similarly, if we evaluate things at low momentum. A C function, well, intuitively, when you integrate out degrees of freedom to go down in the RG, the number of, well, if you're integrating things out, the number of degrees of freedom should go down. But this turns out to be incredibly difficult and interesting when you try to make this precise, this counting of degrees of freedom and this idea that the number goes down. One intuitive way to think about that is anytime you try to calculate degrees of freedom in quantum field theory, you always get infinity. And infinity, once you subtract infinity, well, the degrees of freedom may or may not go down anymore. And that's what makes this difficult. But the idea of a C function is something that's finite and well-defined and counts degrees of freedom. C function is something that's universal at the fixed points. Universal just means that it depends only on the CFT. Something you can calculate in conformal field theory. It doesn't depend on how you got there or what scheme you used. And secondly, it should always be smaller in the infrared. If you find a function like this, then that's a good candidate for something to call the number of degrees of freedom in quantum field theory. So the idea of C theorems was introduced by Zamolodchikov in the late 80s. So Zamolodchikov proved the two-dimensional C theorem. Shortly after that, Carty conjectured a C theorem for 4 dimensions. So the conjecture in 4 dimensions was that a different quantity called A, which I'll talk about, is monotonic under RG flow. But the proof didn't come, or the derivation didn't come until many years later in, I think, 2012 by Komargadze and Schwimmer. So it was a couple decades between the conjecture and the solid argument for the A theorem. Now we also have a 3-dimensional F theorem. And one thing that's interesting about all these is that they all seem to be very dimension dependent. So there are many different arguments for the C theorems, and they depend very strongly on what dimension you're in. The 3-dimensional F theorem, by the way, I should make a disclaimer about all the letters. Okay, so when I call them C theorems with a capital C, I'm referring to this broad class of quantities that decrease under RG flow. But people didn't know in advance what the decreasing quantity was, so they didn't call it C. And so the thing that decreases depends on what dimension you're in. Okay, so in 3 dimensions, there's a quantum information argument for the F theorem. In 2 dimensions, Zamolodchikov's argument is related to stress tensor 2-point functions. In 4 dimensions, Komargadze and Schwimmer's argument is related to stress tensor 4-point functions or dilaton scattering amplitudes. The quantity A came up in a previous lecture. This is proportional to NS plus 11 NF plus 62 NV. So on the one hand, we have all these results in this zoo of C theorems, but on the other hand, I think this is still a very mysterious feature of quantum field theory. So let me try to convince you that we really don't understand C theorems. I need to understand them better. First of all, there's this fact that the argument depends on the number of dimensions. It's a little better in holographic theories. In holographic theories, there's a beautiful dimension-independent argument based on energy conditions in the bulk. But in general quantum field theories, it depends on the number of dimension. So in particular, above 4 dimensions, there's a conjecture that A is still the monotonic quantity. There's a lot of evidence for that, but there's no derivation. Yeah.
Last lecture you mentioned that this combination is lower bounded by 3 series. Does that mean that A is also lower bounded by the value of 3 series?
The question is if A is lower bounded by the free theory. I guess I'm not sure what you mean. The A. So these are the coefficients in the stress tensor 3-point function. In a free theory, this is the number of scalars, this is the number of fermions, this is the number of vectors, but in general, these are just whatever numbers show up in the stress tensor 3-point function, same as when we were talking about the Hoffman-Malthus-Sena bounds before.
But a claim from last lecture is that the bounds are satisfied by 3 series, and it's a lower bound. That is not true.
Well, the individual bounds are saturated by, so each of these has to be non-negative. And the individual bounds on one of them are saturated by free theories, but I'm not sure what the statement would even be when we add them up like this. This is saturated by A equals 0, which is the empty theory.
I think it might be talking about the ratio of A and C being a third.
Uh-huh.
So if there's a C theorem for A, right, then what does that tell us about how C runs?
Good. So the question is, what do we know about how C runs? And the answer is not very much. It's certainly not monotonic. So even long before the derivation of the A theorem, people had considered every possible combination of NS, NF, and NV, and there are counterexamples to every linear combination you could write other than A. Something that's always bugged me about the A theorem and about A is, okay, if you find something that's monotonic, then great, you could call it the number of degrees of freedom, but there ought to be a better reason to call this the number of degrees of freedom. In particular, like, what is this 11 doing here? Why is the number of degrees of freedom of a fermion 11 times the number of degrees of freedom of a scalar? Until we understand that 11, we do not understand C theorems. Okay, so
Could you
yes.
please remind exactly to which class of theories this expression belongs?
This is general. So this is the formula for A in any four-dimensional conformal field theory, where these are for.
It has nothing to do with it.
Sorry.
So not necessarily supersymmetric.
Not necessarily supersymmetric. Yeah.
But we don't have any monotonic function for arbitrary QFTs, which are not conformal.
Well, the whole point of C theorems is that there's a quantity that's the C theorem is a statement about QFT, but the thing that it's telling you is about the degrees of freedom in the UV and the degrees of freedom in the IR. So A is measured in the CFT, and then there's some function that has to interpolate between them in the QFT.
So, but between two QFTs along this flow also there should be a degree.
I wouldn't. The whole thing is one QFT. There's only one QFT on the board, and depending on what momentum we probe it at, we're somewhere on this picture. Okay, so what we're going to do in this lecture is to give one of the derivations of the A theorem, four-dimensional A theorem, the one from the average energy condition, so it's connected to the things that we've been talking about. And this is based on recent work that I've been doing with Greg Mathis over the last couple of years. Part of the reason is to study the C theorems, but really the underlying motivation here is that we've learned a lot about studying things like light ray operators, average null energy, et cetera, in conformal field theories. And the bigger question is, okay, how much of that technology can we take and apply to theories with a mass scale? And this is just some step in that direction. But that's the bigger program, and there's questions about things like Lorentzian inversion. Can you do Lorentzian inversion in theories with a mass scale? How much does the bootstrap carry over to theories with a mass scale? So that's a bigger picture. Before we get into talking about the C theorems, I need to give a lightning introduction to Lorentzian correlators in momentum space. We've talked at length about correlation functions in position space, but this lecture is going to be in momentum space. So in momentum space, the correlators that we're going to be talking about are ordered correlators. So time-ordered, anti-time ordered, advanced, and retarded correlators. The time-ordered one you're familiar with, so the time-ordered correlator O1 up to ON. I won't write down the definition. The retarded correlator, I'm sure you've seen the retarded two-point function, but maybe you haven't seen the retarded three-point function, so I'm going to write that one down. We could do an n-point function, but I'll just write down the two-point function. So the retarded two-point function is some prefactor that's there by convention, minus I to the n minus 1. And then some nested commutators. So there's a nested commutator of O, phi 1, phi 2. And then we add to that the swap of operators 1. I forgot my theta function. So it's a commutator times a step function that enforces that T O is greater than T1 is greater than T2, so that these commutators, things in the commutator appear in order. And then we add to all that the symmetrization in operators 1 and 2.
So n is 3 in that case.
N is 3 in that case, yes. So time-ordered correlators are symmetric in everything. In retarded correlators, there's a semicolon here. The first operator is special, and it's symmetric in all the other operators. But the idea is that we can think about retarded correlators as being response functions that measure the response of this operator O to some perturbation that you do on your system with the other operators. So we symmetrize in those, but O is special. Now, we need to know something about the analytic properties of these momentum space correlation functions for later in the lecture. So first, I want to make the following claim. For Ki space-like, so when we're talking about momentum space correlators, we can have space-like momentum, or that corresponds to Fourier transforming the Euclidean correlator, or we can have time-like momentum that corresponds to Fourier transforming the Lorentzian correlator. For Ki space-like, the retarded correlator GR of K1 up to Kn is equal up to this conventional factor of minus I to the n minus 1 to the time-ordered correlator K1 Kn. I'm going to prove this in a second, but first let me tell you why this is important. So what this means, so this is not true everywhere in momentum space. We're going to be thinking about, just like we did in position space, we're going to be going every which way in the complex plane. And this is not true for time-like, well, it depends where you are exactly, but you can choose momenta where this is not true. There's generally not the same object. But what this tells you is that there's somewhere in momentum space where they're the same function. And that means they're analytic continuations of each other. They're really secretly the same function when you complexify momenta. And the only difference between them is how you deal with the branch cuts. Okay, because if we start out in this space-like domain of complexified momentum space, we just have the same function. And now if we want to go off to some other place in momentum space, it's just a matter of how we go around the cuts. Same as the situation when we talked about the position space correlators. So the consequence is that for complexified momentum, K1 up to Kn in C for the n, so we complexify these momenta, Gr and Gt are analytic continuations of each other. Or in practice, what this means is that they differ only by the I epsilon prescription that you use to deal with the branch cuts. The way to think about this is that, so when we had a similar discussion in momentum space, we were talking about Whiteman functions. Sorry, position space. When we had a similar discussion in position space, we were talking about Whiteman functions. And like how you go around the cuts gives you the different orderings in the Whiteman function. in momentum space is very similar, but for the ordered correlators. So in momentum space, all the different ways of going around the cuts give you the time-ordered, anti-time ordered, retarded, and advanced. But it's very similar conceptually in that we just have all these cuts and we go around the cuts and that tells us which correlator we're on. Okay.
Tom, is there no analog of just unordered correlators that you would think about in momentum space?
There is. There's a Whiteman correlator in momentum space. I'm not going to talk much about the Whiteman correlator. And the reason for that is that we're going to be obsessed with contact terms in this lecture. And Whiteman correlators in momentum space do not have contact terms. The Whiteman correlators are not particularly nice in terms of their analytic properties. So for example, the Whiteman correlators are supported only for momenta in the forward light cone, which means the Whiteman functions have stuff like this in them when you write them to momentum space. So you really they're not analytic functions.
In the position space, we had the special O operator and the others were symmetrized. And in the momentum space, these are just like Fourier transforms of those, right? But is there a K which is special here out of the N?
Not when they're space-like, there's not. There's a semicolon here, but it's equal to this thing that's symmetric. So when they're space-like, it doesn't matter. OK, and I have a derivation of this, but it's gotten mixed up in my notes. Let me find it one sec. OK, I deleted my derivation. I could do it without it. Let's see how it goes. This is a problem of using the iPad. If I had a page, I couldn't delete it. OK, so somehow I deleted it. OK, so here's the derivation. I'm going to mess up the I's, though. That's the only problem with doing it this way. OK, so let's look at the retarded two-point function of two operators, O1, O1 and O2. So it's very easy to derive the following identity, that this retarded two-point function is equal to a time-ordered two-point function of O1 and O2, plus, it might be minus, this is the problem, plus or minus, let's just not worry about the signs. I'll write plus O1, O2. And it doesn't matter here if I'm in momentum space or position space. Let's do this in position space. X1, X2, everything's in position space. So this is trivial to derive. You write out the retarded correlator in commutators, and you expand out all the terms. And you do the same thing on the right. You write this out with all the step functions and expand out all the terms. And these are just the same set of terms on the two sides. So this is trivial to derive. And now we're going to go to momentum space. So when we go to momentum space, what we would like to show is that this term drops out for space-like momenta. Now this term is a Whiteman correlator. They're just ordered as written. And the important thing here is that physical states have physical momenta. So k squared has to be time-like, and kt has to be forward pointing. OK, so physical states have to have this type of four momenta. And that means if we look at the operator O of K1, let's call that O1 of K1, O2 of K2, acting on vacuum, then by momentum conservation, so I'm thinking of this really as operators acting on states now. Now, this is the vacuum state, and by momentum conservation, the only states this can make are states with momentum k1 plus k2. And if k1 and k2 are space-like, then and k1, yeah, if k1 and k2 are space-like, then sum is, I should have written their sum is also space-like. If k1 and k2 and their sum are all space-like, then there just aren't any states that you can make this way. Okay, so this is equal to 0 if k1 plus k2 is not a physical momentum. So if we go back to our discussion of the two-point functions, it means that when we have momenta that are not in the physical regime, that the retarded correlator and the time-ordered correlator can still be non-zero, but the Whiteman function has to vanish, and therefore the other two are equal. So I've just given this derivation for the two-point function, but there's a similar argument that you can go through for any correlation function and show that these two correlators are just the same when the momenta are space-like. So I think I meant to also specify that the momenta appearing in intermediate states are also space-like in order for this to hold. Yeah.
Don't do this active for single operator, right? And then every moving to outside the forward-like cone with an annihilated ground state.
Yeah, that's right. So something like this. If that k is not inside the forward light cone, this is 0. The reason the time-ordered correlators can still be non-zero is that the time ordering is done inside the you do that inside the Fourier integral. You time order inside the Fourier integral, so there is no operator acting like this inside a time-ordered correlator. Yeah. Other questions? That's just convention. That's part of the definition that entered here. Over here, we had n equals 2, and I was, so that was this I here. Other questions? Okay, with that background, now we're going to go back to the C theorem. The first step.
For higher point correlators, when you obtain some terms that are like T something, so products of time ordering.
Yeah, when you do this for like a 3-point function, there's like 8 terms on the right, but they all go away except for, yeah. So the first step toward the A theorem is to find a CFT formula relating A and the average energy. So we're going to start out, in fact, 90% of this discussion is going to be in CFT, and then we're going to do a magic trick in the end and get an answer that's for our G-flows. Okay? So we're now talking about CFTs in 4 dimensions. In a CFT, the trace of the stress tensor, which I'll write as T, so this is G mu nu T mu nu is equal to 0. It's traceless. This holds, we say this holds as an operator equation. As an operator equation. So when we have equations like this for operators, it means that they hold inside correlation functions up to contact terms. You're not allowed to use things like this inside a correlation function, but you are allowed to use it up to contact terms. So this holds in G up to contact terms. So to understand the contact terms, we can start by writing down the trace anomaly. So the trace anomaly tells us the trace of the stress tensor in a CFT in an arbitrary metric G mu nu. And the things that can show up on the right-hand side is everything that's allowed by dimensional analysis. Okay, so in conformal field theory in 4 dimensions, the stress tensor is dimension 4. And the things that we can write on the right-hand side need to be built out of the metric. So they need to be curvature invariants of dimension 4. There are 3 of those. So the first one is called Euler. So this is some combination of R squareds, of curvature squares. The second one is a Weil invariant squared. And the third one is box R. And this has coefficient B1. Actually, there's a fourth one, B1 prime R squared.
They couldn't call it B2.
Well, these don't, only the first 2 have names. The other ones, I have to make up names, and I'll explain why in a minute. There's other things you could write. So you could write something like this, where lambda squared is the UV cutoff of your theory. Or you could write B3 lambda to the 4th. So these things are all OK by dimensional analysis. So first of all, this one is not allowed. This one is eliminated by what's called Weil consistency. And Weil consistency is just a way of saying that the stress tensor, the trace 2-point function should be symmetric. So remember that at this point we're in Euclidean signature. Euclidean correlation functions should be symmetric. And if we demand that the 2-point function is symmetric, I'll calculate in a second. If we demand this 2-point function is symmetric, that eliminates the R squared term. Now, these 3 terms, yeah.
Are we in a CFT now or in a QFT?
CFT.
But then what is this cutoff?
Well, CFTs have a UV cutoff. I'm gonna comment on this in a second. Yeah. Okay. So these terms can all be removed by adding counter terms to your action. So these are all of the form G mu nu delta delta G mu nu of something. And that means that you can pick a renormalization scheme where these terms drop out. And that's usually what we do in CFT. So usually in CFT, when we write down the trace, well, it's really the first 2 terms, the trace anomaly, because there's no counter term that eliminates them. The other terms are just some other terms that could show up depending on your renormalization scheme. Is your question?
Yeah, it's confused, like, because the whole anomaly is supposed to be like exact because it has to derive from like very fluid expansion. Like, is it all supposed to come from like a variation with fixed?
Sorry, this is something local. So the effective, if you have local terms, that will come from something non-local, so that's physical, yeah. I need to keep these terms actually for the argument that I'm going to give. And the reason for that is eventually we're going to talk about RG flows. And when you have an RG flow, you can pick a scheme where these vanish, where these are set to 0 in the UV, but they'll be generated by the flow. And that happens. What'll happen is that this will, like if you integrate out a massive particle, you'll find a term here in the infrared CFT that has a m squared r in the trace, and another term that has a m to the 4th. So these terms do get generated under our G-flow, when we consider our G-flows, we're only allowed to tune once in the UV. So I need to keep these terms. These I'm just going to ignore because I don't want to talk about them, and they're easy to get rid of because dimensional analysis. But this one I'll keep along for the ride a little bit so we see how it enters. Yeah.
We're ignoring the terms that go to 0 as lambda goes to infinity, like 1 to the 4 over lambda.
Yeah, we're going to take the UV cutoff to infinity, so those terms drop out. So for example, if we're say we integrate out a massive field, and that generates an r to the 4th, or let's say that generates a r cubed over m squared. Well, when you go to the infrared, that term, you don't see that in the infrared. So that's not part of the CFT. It's part of the QFT, but it's not considered part of the CFT, which is kind of like setting m to infinity from the infrared point of view. Yeah?
So B2 and B3 will also be generated by the flow, but we're just ignoring them because that doesn't change the discussion.
Correct, yeah. Okay, so that's our A, and our goal today is to show that A decreases under RG. But as I said before, our first goal, the first step here is to find a formula for A just at the conformal fixed point.
Thomas, this definition of A will give the same 1162 stuff in.
Yes, this is that A. This is that A, exactly. Yeah.
But there we defined it as a TTT correlation function. We found out NS and F.
That's right. So you could ask, why is it showing up in two places? And the answer is there are ward identities that relate the TTT correlation function to the contact term. Yeah, but it's the same A. Yeah. This is really more like the definition of A. A is by definition the thing that shows up in front of Euler in the conformal anomaly, and then you can go through some ward identities and show that it also shows up in those stress tensor 3-point functions that we talked about before. So this is the trace anomaly. This is the stress tensor in an arbitrary background. But now we can use that to calculate any correlator that you want that involves at least one trace. Trace is 0 as an operator equation. So it's 0 as an operator. So we expect any correlator involving the trace to be pure contact term, just a bunch of delta functions. And that's exactly what we're going to get. So let's calculate one. T of x2, T of x1. I don't have to take the trace here. We could put some other stress tensor here, T mu nu. But I'll just do the trace. The insertion of the stress tensor, you can do that by doing a variation. So the convention is that variation is -2 over root g of x2, g mu nu of x2, delta g mu nu of x2. So we could think of this as two variations of the effective action, but we've already done one variation up there, so let's just think of this as one variation of the anomaly. So we put in here root g of x1, t of x1 in a background. So this is our formula for the stress tensor 2-point function. And this is easy to, so it's easy to do this variation. You just have to vary, you have this bunch of curvatures up there. You have to vary the curvatures with respect to the metric. And just do this metric variation. If we do those variations and then at the end of the day, we set G mu nu to flat space, so you do the variations first, and then you set to flat space, you find minus 6 d1 d4 of the four-dimensional delta function of x1 minus x2. Okay, so that's a good exercise to work through.
Isn't the first equation also a correlator and therefore should only allow contact terms?
Good. So what we mean is that only local terms are allowed in the correlator, meaning everything on the right-hand side has to be at one point. So everything on the right-hand side there is already at one point. It's all at point x. And the point is that things, when you go to like here, you might have thought this was going to be a function of 2 points. The fact that it's 0 means that it's really all at 1 point. So this is our contact term. Now, I want to ramble a minute about contact terms because I always found them very confusing until working on this project, really. Okay, so what's with contact terms? Usual correlation functions you can interpret as operators acting on states. Like, you could put these states in, and then the operators act on the state, and then you take some overlap of those states. Okay, contact terms aren't like this. It's a fact that the stress tensor trace is 0 as an operator. If you use the operator formalism, then it's 0 as an operator, and T of x acting on the vacuum is 0. That's the state it is. Okay? So you cannot calculate contact terms like this by thinking about an operator acting on a state. That's not what contact terms are. Contact terms are a shorthand or a bookkeeping device for telling us not what operators do in our theory, but for what operators would do in a nearby theory deformed by adding some sources. Okay? So when you see an equation like this, this is not telling you something about the operator t. The operator t is 0. It's 0. It can't have nothing can happen. This is telling you what would happen to the operator t if you were to turn on a background metric. And we should think about contact terms in that way. So for example, if I were to stick an ANAC in here, then that doesn't need to be positive. The ANAC is positive as an expectation value in quantum states in your Hilbert space. And when we're talking about contact like this, we're not talking about operators that were produced by acting on states. So we have to be careful about that. But we can use contact terms. We can think about contact terms as telling us about this slightly deformed theory. And so we just should keep that in mind. Let's go to momentum space. Well, that's really easy for contact terms. I can do that Fourier transform probably in my head. T of K1, T of K2 is equal to minus 6 B1 K to the 4th times the momentum conserving delta function K1 plus K2. So contact terms are local in position space, meaning all delta functions, and they're analytic in momentum space. So we got a polynomial in momenta, because it's these polynomials in momenta that become local terms in position space. Yes?
Sorry, why does the delta function not become like a phase?
A phase?
Take the Fourier transform of the delta function.
The Fourier transform of the delta function by itself would just be 1. But then the derivative is coming in. So the Fourier transform of the delta function is 1, and then this comes in and gives you a k to the 4th. Now I'm going to skip some steps because the next thing I want to do is I want to calculate a 3-point function. That's a pretty messy variation, but I'll just tell you what you, my chalk. I'll tell you what you would do. So you would vary again. The 3-point function that we're going to be interested in has 2 traces and 1 null energy. So you vary again, this time with respect to GUU. Now, we're going to want to discuss the average null energy condition, which is something that makes sense in Lorentzian signature. So after you do this variation, then you're going to wick rotate. If you take a Euclidean correlator and you wick rotate it in this sort of standard way where you just rotate everything gradually by I, then that gives you time-ordered correlation functions in Minkowski momentum space. And actually, we want the retarded correlator. But from the discussion earlier in the lecture, it's very easy to calculate the retarded correlator. Because we're talking about contact terms. So remember what we said in our discussion of momentum space correlators is that they are just related to each other by analytic continuation around branch cuts. Now, contact terms are analytic. What that means is that all of the different orderings have the same contact terms. So up to those conventional factors of I, which in this case is just a minus sign, the contact terms are all the same. And you don't have to worry about any branch cuts. And at the end of the day, if you do this calculation, then here's the correlator that you get. So let me write the ANAC operator as script E. So this is integral du TUU of u equals 0 and x equals 0. We're taking this ANAC operator and just sending it right through the origin in Minkowski space. And what you find from this calculation is the retarded correlator of the ANAC and 2 traces is equal to 32 pi a k1u squared k1 dot k2 delta of k1u plus k2u plus stuff times k1u squared k1 squared plus k2 squared delta k1u plus k2u. The second line won't matter, so feel free to ignore it. The important thing is that just by doing this, okay, it's a sort of a pain to actually do it, but it's a very straightforward mechanistic calculation that we're talking about here. You just vary the trace anomaly twice. You do some integrals and put it in momentum space, and you find that this Anek trace-trace correlation function has an A in it. Okay, so that's promising. That's what we were hoping was to have some relationship between A and the average null energy. Are there any questions so far? Sorry?
Sorry, did you say B1 is independent because you can change it with the counter term?
Yes. There's a B1 in stuff. Yeah. Other questions?
What is ultimate theta B1 here?
Sorry?
What is ultimate theta B1 here?
Well, it's going to drop out, but it's in this stuff term. The important thing of the stuff term here is, okay, there's two different momentum dependencies on the first line and the second line. So the first line has the k1.k2 term, and the second line has no k1.k2 term. So you can disentangle what's going on with A and what's going on with B1, and this is also where B2 and 3 show up, if we had kept them.
But like B1 is fine, like satisfied with Sumino and everything.
Yeah, the reason we are happy to get rid of B1 is because we're looking for some universal statement about conformal field theory. So like the C function is not allowed to include a B1 in it because it can be altered by counter term. It's not intrinsic to the CFT.
So why didn't you go with the same pocket as the yellow terms? The lambda terms were also like adjusted by local counter terms.
Yeah, these can all be adjusted by counter terms. Well, I don't know about this one. This one's eliminated by Weil consistency, and the other three can be adjusted by counter terms.
Right. So those three are exact, and the last one's not both, I guess.
Sorry, that's like, yes, yeah.
So just so I understand, the reason we don't care about terms that differ that can be generated by local counter term is those are just telling us how we're approaching the CFT, whereas the A and C are about the CFT itself.
Okay, so the comment is the reason we don't care is because they're about how we're approaching the CFT, not the CFT itself. Yes, but I would rephrase it slightly. It's not that we don't care. It's that they're not allowed in our C function because that's not a property of a CFT. And so we have to try really hard to make sure they drop out of all our calculations. Like if we end up proving something about B1, that might be nice. It might prove something about RG flows, but it won't prove anything about the properties of the endpoints, the CFTs. So that wouldn't give us a C function. It might give us some quantity that increases or decreases, but it's not a C function. Other questions? Okay, we're still in CFT at this point, but now I want to take the results that we have so far and write a formula for A. In other words, I want to take this equation we have here, and I want to turn it into a formula for A. I want to solve for A. This is actually easy. Okay, so to solve for A, we can just write A is equal to some coefficient times dk1u squared dk1 dot dk2 of the momentum space correlator, which I'm going to write out as the Fourier transform. So d4x1, d4x2, e to the I k1x1 plus I k2x2 of the retarded correlator and then all evaluated at k equals 0. If we look over here and we do that on the right-hand side, then what those k derivatives are doing is just extracting the A term and getting rid of the stuff term that we don't like. That's why it was important that there was different momentum dependence in the A term as compared to these non-universal terms that we didn't want. So that's just trivial. And now I'm going to bring the k's inside the Fourier integral. So each one of these dk's just brings down some x's. So I'm going to bring them down and set k equals 0. And that gives the following formula. Now I'm going to put the constant back in. A is 1 over 64, integral d4x1, d4x2, u1 squared, delta of u2, x1 dot x2 times the retarded correlator of the ANAC with t of x1, t of x2, and that's it. Let's put a box around that one. That's the formula we were after. I don't want to keep writing this factor that shows up in here, so I'm going to call that k. That's our integration kernel. And the point is that if we pick the right kernel, then we can extract A from this ANAC correlation function. Now, this is in CFT. Okay, let's emphasize that. This is in CFT. And this formula is kind of trivial because the right-hand side has traces in it. So this correlator is just delta functions. This thing's pure delta functions. It's like a nasty full page long of delta functions if you write it out, but it's just a bunch of delta functions that you get from the anomaly. And all this formula is doing is it's picking off the coefficient of one of those delta functions by integrating against a kernel, okay? We're done with CFT. Any questions so far? We're ready for our G-flows? Actually, C dropped out. There are B's in there, but there are no C's. The reason there are no C's is because we did 2 trace variations. And so C was the vial term in the trace. And if you do so the vial term is vial invariant. So if you do a second trace variation, C drops out. So there's no C in this expression. So now we'll return to this picture where we have an RG flow from the UV to the IR, and we'll have call the mass scale of that RG flow M. And what we're going to do is we're going to take this formula and apply it to the infrared CFT. Okay? That's easy. All we have to do is write IR on it. So let's do that. Okay, still true. But now we're going to use the important step. So the important step is that this correlation function in the infrared CFT, you can also view this as a low momentum correlation function in the QFT. So let me write that out. We can use the fact that GR in the IR CFT as a function of K is equal to GR in the QFT for momentums K squared is much less than M squared. One has to be a little careful with improvement terms in the stress tensor, but they drop out. I'm not going to include them. Okay, so that means that we can go back to our formula over there and replace that CFT correlator by a QFT correlator. So let's write it again. We have AIR is equal to 1 over 64, the integral over x1 and x2 of the kernel times the retarded correlator of ANEC, t of x1, t of x2, now in the QFT. The fact that we're doing this integral over all x is basically is the same as evaluating at low momentum. Remember when we wrote down when we derived it, we took some derivatives and then evaluated at 0 momentum. So this is a low momentum expansion that we're talking about, and we're free to use the QFT correlator in that expression. That was the most important step, because now what we've done is we've taken a trivial formula involving delta functions in a CFT and replaced that by a not trivial formula, because this is not a delta function. So this is an honest to goodness correlation function with contributions at separated points. It's a whole function of x1 and x2, not just contact terms. So what is the structure of this 3-point function in the QFT? If we say we take this 3-point function in the QFT and we go to very short distances, let's look for contact terms in this 3-point function. So we take x1 and x2 very close to each other and put them right on top of the ANEC. Well, now we're talking about the UV CFT. We're talking about short distances, so we're talking about the UV CFT. So the structure of this 3-point function is that this is UV contact terms plus separated points contributions at separated points, non-contact terms.
Could you repeat why the I? You said something about there we have taken k equal to 0 limit, and that's why the IR correlators of the CFT are the same as the QFT.
Yeah, because what this integral is doing is it's pulling off the k to the 4th term in an expansion in momentum. Imagine you had the full-blown momentum space correlator and you just started doing a series expansion in momentum, k to the 4th, and then it would be like k to the 6th log k squared, et cetera. This is pulling off the k to the 4th term. It's the leading term at low momentum in this correlation function, and that's controlled by the IR fixed point.
But the correlator that is there in the curly braces is like a position space correlator, right? That is like for the full.
Yeah, but when we do this integral, that's the same as saying let's just pick off the k to the 4th term in the momentum space correlator. So it's the fact that we're doing the integral is what allows us to replace this here. Other questions? Yeah.
Is there here any difference between the UV contact terms and just contact terms? What is the meaning of that term?
Well, no, you're right. Contact terms are always in the UV. Maybe this is for emphasis because of the next step I'm going to do. Okay, so let's ask, what is the contribution to this integral of those contact terms? Well, those came from the UV. They're controlled by the UV CFT, so we can use our CFT formula again. And so the contribution here from the contact terms is AUV. And I'm going to take that contact term and I'm going to move it over to the other side of this equation and write it as AUV minus AIR is minus 1 over 64 integral over x1 and x2 of the kernel times the retarded correlator. But now with the rule that you have to do this ignoring the contact terms, because we already moved those over. So there are two contributions to these. So the way to think about what's going on here is that the total anomaly in the infrared has two contributions. It has a contribution from the delta function in the UV, and then it has some contribution from what happened along the flow. The way I like to think about this is that there's some delta function like this in the IR CFT. And the size of that delta function is AIR. I'm being schematic here. There's a million terms here. There's lots of delta functions. But there's this particular term, the interesting one, is some delta function of height AIR. And then if we zoom in on it, this is drawn in position space. So this is like at coincident points from the infrared point of view. But if we zoom in on this picture, then what we'll find is that there are actually two types of terms here. There's a UV delta function, and then some contributions from separated points. So this is AUV, and this is the separated stuff.
Sorry, can I ask you something? In QFT comes, there be like divergences there that one is to deal with somehow?
Divergences in this UV, these are all renormalized correlators. Everything is a renormalized correlator. So no. Yeah.
Here it seems that we're computing some IR quantity, and the dominant contribution to it is from some UV quantity plus lesser contribution from the IR stuff. How do I reconcile this with the usual RG intuition of low energy things mattering most?
Yeah, the question is, why is UV stuff contributing to an IR calculation? And I think we have to be a little careful with that intuition. The IR is always like, the UV has a huge impact on the IR. That's where the IR came from. It's just that you don't see the microscopic details. And that's exactly what's happening here, is that there's, from the point of view of the infrared CFT, this is all UV. Everything in the RG flow is UV. There's some UV stuff that came from the literal UV fixed point, and then there's some other short distance stuff that came along the flow. But the point is that when you zoom out, you don't really see this fine-grained structure. Like if you zoom out on this delta function plus blob, and you zoom out far enough, all you can see is this slightly weaker delta function. Because you're going to end up, if you imagine integrating some test function against it, it can only see this delta function. It can't really see this short distance structure. Other questions? Yeah.
Why are you drawing this AUV longer than AIR?
Well, I'm about to argue that the right-hand side is positive, and so A is decreasing.
So, but that's not. So the thin part is not just representing the contact term.
The thin part is the contact term.
But the contact term would exactly cancel. So why are they not just look the same?
In the QFT, the contact terms exactly cancel. Okay, so this is a picture of the QFT, and in the contact terms of the QFT is just the delta function, and that agrees with the contact term of the UV CFT. But the contact term of the CFT, the infrared CFT, does not agree with the contact term of the UV CFT, because they have different anomalies, and the anomalies control the contact terms. So the infrared contact term, from the point of view of the RG flow, is some UV CFT stuff plus some QFT stuff along the flow.
So the spawn here is not the separated point. It's still the contact term.
From the point of view of the QFT, it's separated points. So it's coming from this here is our QFT correlator. And I'm plotting this function as a function of x1 minus x2, say. So it really is coming from separated points in the QFT. But the point is that in the infrared CFT, the infrared CFT just thinks that's all context stuff. Imagine you have some function. Maybe it would be helpful if I don't know. Imagine you have some, okay. You have some correlator, which is a function of k squared, and it's not an analytic function. It's some complicated function that has all sorts of non-local stuff in it. But then you do a series expansion in k squared, and you discover that the leading term is k to the fourth, and then maybe plus, let's say, k to the sixth log k squared, stuff like that. This is the kind of thing you'll get if you actually calculate these correlators. Then this looks like a contact term, even though it didn't necessarily, it wasn't necessarily a contact term until you started doing the series expansion. And that's kind of what's happening. The CFT knows about this term and thinks it's a contact term. The QFT knows it was really part of this non-analytic function that you're series expanding. Other questions?
Got about 6 minutes.
Okay, I only need one. Good. Yeah?
How do we know that the UV contact terms factorize from the separated points contribution? It's not something.
Yeah, so how do we know that they factorize? You're asking, how do we know I can really split off the delta function from the other stuff? That requires being more careful. Is very subtle, and it has to do with the fact that the ANAC operator is particularly well behaved, but I'm not going to have time to get into it. Other questions? Okay, so this is basically it. The only thing that we still have to do, so we have expressed everything in terms of this correlator. I'm going to write that one more time. AUV minus AIR is integral k dot t of x1 ANAC t of x2 in the QFT. Okay, so the only change compared to over there is I changed a retarded correlator into a Whiteman correlator. And the reason that I can do that is because the ANAC is special. So if you take this retarded correlator and you write out all the nested commutators and everything, then you'll find a bunch of terms. Well, you'll find that Whiteman term, and then you'll find a bunch of terms where the ANAC is sitting next to the vacuum. So I used the fact that the ANAC annihilates the vacuum in both directions in order to get rid of all those extra terms and reduce this to a statement about Whiteman functions. The good thing about Whiteman functions is that now you can interpret this as operators acting on quantum states. This is the first time, so all these correlators, you couldn't really interpret that way because there were all these contact terms and everything. But at the end of the day, because there's no contact terms anymore, and this is a Whiteman function, you really can interpret this as honest-to-goodness operators acting on the Hilbert space. And with a little bit more work, you can show that this is the expectation value of the ANAC in a state where that state is just some wave packet that you make, like e to the I kx t of x acting on vacuum. It's very similar to the wave packets that we were using when we discussed the Hoffman-Maldacena bounds. Now we've expressed this change in the anomaly in terms of something that's positive by the ANAC. So this is positive by the ANAC. And therefore, AUV is bigger than AIR. And that's what we were after. That's right. This is sort of the weakest version. Yeah.
So do we have some stronger version?
Good. So the question is about the weak versus stronger versions. So not from the ANEC, we do not have a strong version of the C theorem. From Komargovsky-Schwimmer, you can get something that looks more like the strong version, where there's a. So the strong version for everyone else is you might want to not only find that the AUV is greater than AR, you might want to find a function that's well defined along the flow that monotonically decreases from AUV to AR. This method doesn't give us that. I'm not sure why, actually. That's actually something we're still thinking about. Other questions? Yeah. It doesn't feel like it, does it? These C theorems are very mysterious. Let me tell you what I wanted to be true when we started this project, and then I'm not sure how it relates. The intuition that started this was trying to think about Hartman in a quantum field theory as opposed to a conformal field theory. And something you could try to do with Hartman is create this state. So remember we had like a fireball and we had our light ray. Something you could try to do is you could ask, well, what happens as we move the detector farther and farther away? And you might think that if you have it pretty close, that you're effectively doing Hartman at the UV fixed point. But if you do it very far away, those massless particles won't be able to get all the way out to null infinity. Only massless stuff can get out to null infinity. And so that if you did it in here, you'd be doing Hartman at the UV fixed point. You do it over here, it's Hartman at the IR fixed point. And you would also think that, well, surely if I move my detector farther away, it's only going to get less. It's only going to measure less energy. Less stuff will hit my detector. So that would have been very intuitive, but I don't really know how to attach those words to this calculation. It was kind of a reason to try thinking about the ANAC, but in the end, the calculation I've described doesn't seem to really match onto that. So I don't know. I would really love to have a more intuitive way of thinking about it where it's obvious, like this is degrees of freedom and it's obvious it had to go down as opposed to, what we have. Yeah. Other questions? Yeah.
So the proof of the ANAC from yesterday was strictly only in a CFT, right?
True.
And you were applying it in a QFT.
Yeah, that's true. So here the assumptions of yesterday do not apply. I believe that the assumptions of the Faulkner and collaborators' proof from relative entropy do apply. So we could apply that ANAC, or we could just say that if you assume the ANAC, then it gives the C theorem here.
The other proof of the ANAC, the first proof of the A theorem, did that use this method to do it, or was it an independent?
The proof of Komargovsky and Schwimmer is very different. And in fact, I think it's a very interesting question to compare and understand how they're related, because this is a 3-point function involving light ray operators. What they did is some 2-to-2 scattering amplitude. It just feels completely different. But somehow we got the same delta A.
So does their A theorem imply the ANAC in the QFT if you do it the other direction here?
Does their A theorem imply the ANAC in the QFT? It does in this particular state. Yes.
Oh, I see.
Yeah. Yeah.
So it feels like with this proof, something a little stronger is true, that not only are you seeing that the anomaly is going down, but also the exact amount it's going down by is related to this particular state you're evaluating the ANAC in. Is there any intuition more for like the properties of this particular state? Is there anything we can say, or is it just pretty
No, I mean, vaguely I could say that, well, this state is created by doing a Weyl deformation in some way. And it's kind of natural that you can measure anomalies by doing Weyl deformation and measuring the response. But why why exactly like this, that I don't know. I think we're out of time. We can continue discussing. But I also think that since this is the last session, I would like to really thank the organizers, both local and non-local, and let's all give them a big hand of applause.
Thank you very much, Tom. And let's not forget to thank Tom for this lecture and his whole series of lectures. And yeah, so we have reached the end. There's a few other people that Ethan and I would like to thank. So let's see, we would like to thank Willie and Vimal and behind the scenes Skip Woody for doing all the AV stuff, making sure the TASI videos got on YouTube. So thanks to them. I know Tom just acknowledged them, but I'd like to again thank the scientific organizers. So David is here, also Clay, also Sasha, for everything they did putting together this wonderful program for the school. So thank you all very much. I would like to thank very, very much Maura. So Maura, anytime you emailed tassi@colorado.edu, Maura was who you were talking to. She's done so much work behind the scenes to make this school work. I'm so grateful to everything you've done, Maura. Thank you so very much. And I think very last, I would like to thank all of you. At the opening sort of orientation, I remember saying something along the lines of, you're going to learn a lot from the speakers, but you may find that the people you learn the very most from are each other. I think this has been a spectacular TASI class. So look around and please give a round of applause to all of your fellow students. It's been great getting to know you all. And I'm looking forward to seeing you all at seminars, at conferences, maybe someday some of you all lecturing at TASI up here. So thank you very much. Have a great trip home. It's been wonderful. Thanks a lot.